What makes photonic qubits difficult to scale? Imagine trying to build a giant puzzle with tiny, delicate pieces that can easily slip out of place. That's similar to what scientists face when working with photonic qubits in quantum computers. These qubits use individual photons to carry quantum information, and while they have some big advantages, many hurdles make scaling them up a real challenge. First, photons tend to get lost along the way. When they travel through tiny waveguides, beam splitters, or couplers in a photonic circuit, some photons don't make it to the end. This loss reduces the accuracy of quantum operations and makes it harder to keep the system reliable as it grows larger. Even small losses add up quickly when you're working with many photons and complex circuits. Second, creating single photons on demand is tricky. Many current sources relying on probabilistic methods, like spontaneous parametric down conversion, which sometimes produce no photon or more than one photon at a time. More reliable sources, such as quantum dots or cavity-enhanced emitters, need very precise fabrication and integration. Making sure these sources produce identical, pure photons consistently is a big technical challenge. Third, two-photon interactions are weak naturally. Photons don't easily interact with each other, which makes creating entangling gates, necessary for quantum computing, difficult. Researchers often use measurement-based techniques or extra photons to get around this, but these methods requiring more resources and add complexity. Developing materials or mechanisms that strengthen photon-photon interactions is an ongoing effort. Fourth, connecting many photonic chips or modules is complicated. While integrated photonics helps make circuits smaller, scaling up means linking many components with minimal loss and precise control. Current systems show promise but still suffer from high losses and imperfect parts, which limit how many qubits can work together reliably. Fifth, error correction and fault tolerance need extremely low error rates. Photonic systems requiring components with very high quality and minimal loss to implement error correction codes. Achieving these low error rates across thousands or millions of qubits is a major engineering challenge. Additional issues include managing control electronics and classical systems that operate the quantum processor, as well as maintaining coherence over many photons in noisy environments. Despite these difficulties, photonic qubits are attractive because they can operate at room temperature, transmit data at high speeds, and potentially create large entangled states. Researchers are working hard to improve photon sources, reduce losses, and develop scalable designs, all aiming to turn photonic quantum computers into practical tools for the future.